particular focus on text processing in Watson. Watson is a system that won a competition. Okay, the competition is called Jeopardy. It's a televised show in which contestants try to answer questions. Okay, so Jeopardy is a televised show, a very popular one, in which contestants answer questions on all possible topics. They also try to solve puzzles, sometimes multiply some numbers fast. It's supposed to be fun. Many of these questions are challenging. They are challenging on two fronts, and we're going to see some examples in a minute. They are challenging because of the language, which is of interest to us as computational linguists, and they are also challenging because they require a large knowledge of various facts. Okay? So around 2006, a group that I was previously connected with decided that they would like to try applying language technologies to question answering in this very broad domain of Jeopardy questions. I joined the project in 2008, and in 2011 we had a live competition between two previous champions of Jeopardy, human champions, that is Ken Jennings and Brad Rutter. Watson won this competition, but it wasn't clear until the very end that you know, the machine is good enough. I mean, the whole game was actually quite nerve-wracking. We didn't know, you know, that the machine would win, and definitely we didn't expect that it would win, you know, at the score of 77,000, say, to 24,000 and then 21,000. So I'm going to say a few words about what's behind this technology and what's the methodology that we use to develop this technology and to extend it and apply it to other domains such as medicine and in parts of business. All right, so Watson was a machine, okay? It was a relatively powerful machine. It had almost 3,000 little cores, okay? 15 terabytes of memory, operated at 80 teraflops, so essentially it was a supercomputer. Of course, I mean, as with any such machines and any such technologies, I mean, this is eventually going to get miniaturized, okay? I don't think it's going to be on your smartphone anytime soon. But look, I mean, some people are speculating that you could connect your smartphone to a machine like that and have your questions answered. Right? So anyway, why did we need such a big machine? I mean, some of it was for redundancy, and some of it is because language processing is difficult. And essentially, this shows how difficult language processing is in some sense. I mean, if you try to answer a question, you know, on a regular workstation, it may take up to 2 hours. But if you need to answer in real time, it requires really a much more powerful hardware. So let's see what's happening there. But before we go there, let's you know, so just a couple of obvious things. Okay. So first of all, language is interesting and difficult because it is implicit and meanings are contextual. All right. So here is one example. Say if you have a database of where people are born, or you know, or on Wikipedia or something like that, you essentially can form a relatively simple query one of the formal languages and get an answer. On the other hand, if the knowledge is distributed over textual resources, you can have a sentence like the one below, in which says that one day from among his city views of Ulm, Otto chose watercolor to send to Albert Einstein as a remembrance of Einstein's birthplace. Okay, and so how do we get from the question, okay, to where Einstein was born, yes, to this particular passage, yes, since there are many passages that mention Albert Einstein, and born, okay, as a keyword here is not even mentioned here. All right, so we have to get to this passage and then extract, make the connection that that from the very beginning of the sentence, where in the second clause we have Ulm, the last word, birthplace, connected to born, and and essentially create the answer. So that is the challenge, and essentially Watson was built to address these kind of challenges. That is how to get from the implicit meaning to the clear answer to the question. So here are some examples of Jeopardy questions. Say for 1000, we have the first person mentioned by name in the iron mask is the hero of the previous book by the same author. Okay, so what does it all mean, and how do you even parse this sentence as a human so that you can answer it, in real time, say, and press the button that you want to answer this question in under a second. Okay, so you can see these kind of questions. These questions, the answers to these questions will not necessarily appear in any particular source. Yes. So, for instance, for 2000, we have of the 4 countries in the world that the U.S. does not have diplomatic relations with, the one that is farthest north. Okay. So this requires some synthesis. Yes, we could probably find a list somewhere of the countries that the U.S. has or does not have diplomatic relations, but of course they will not be ordered by how close to the North Poles they are. So the challenge here is that the language is difficult, the questions are challenging in all kinds of ways. It requires high precision. You get penalty, okay, if you decide that you want to answer and then you make a mistake, a certain amount of money is going to be subtracted from you. And it has to be done fast because people can answer these questions very fast. All right, so briefly, what it is that Watson does. So we take a question such as this. We produce the answer. Okay, we produce the answer with confidence. So the confidence is sort of normalized from 0 to 100%. We always produce. We show 3 answers, but we produce usually between 50 and 200 candidate answers. Okay, so which we don't show. Most of them are completely nonsensical. Okay, but usually the top is the more reasonable. So how do we do that? Well, we take the question, we analyze it, we generate hypotheses, we evaluate the evidence, we combine the evidence, and we produce the answer. Let's talk a little bit about it. Okay, so in question analysis, we look at what it is that the question requires. So in this case, the question, we parse the question and we try to find, this is supposed to be, the type of the answer, okay? So lexical answer type, that's what we take. So in this case, it's a place. So we're going to be looking for a place, but place is not necessarily a city, okay, and based on that, we retain this information. Then we use the question to essentially create a collection of searches or to create the hypothesis. So essentially we use the, a search engine or search engines to find entities that mention in their description, one or more keywords or key concepts in the question. So in this case, happily enough, all of these entities are cities, okay? But in many other cases, the types of these entities may be all over the world, all over the map, yes. Then for each of these entities, we look at the evidence behind it, that is, how are these concepts connected with the concepts in the question. We produce about 400 or more scores that we associate with these entities, and then we weigh and combine these scores to create, the final score. And then if the score is about certain threshold, we try to answer the question. Right, so you get, different entities have different scores, and there is machinery, which is essentially a logistic regression based final scorers that produces the final number. And if this final number is bigger than 0.7, we answer the question. What do they do? Okay, so let's see. Sorry?
Just like the first case.
Oh, okay. All right. Oh, that went too fast. Okay, so questions very often require a combination of information from different sources. So for instance, if you have a question, when 60 Minutes premiered, this man was US president, so we are looking for a person. But of course, the answer will not be present in any source. So what we do in these cases, we divide the question into clauses. We essentially try to find information associated with these different parts, and then synthesize the answer based on these pieces of information. Another thing that's happening, which is interesting and important, is that the system can learn from prior mistakes. So for instance, here what we have is a question about celebrations of the month, okay? And what you see here is generated Watson answers, which do not make any sense. So the clue is D-Day anniversary and Magna Carta Day. So we know that we are looking for a day, but we can't find, what the answer really is. Okay. So the problem is that Watson thinks at this point that the answer type should be a day. So it comes with a document about Rimini, which probably mentions some of these words, and but of course it is below the threshold. Okay. Then we have National Philanthropy Day and All Souls Day. Okay, well, it comes with the answer Day of the Dead, which is a little bit more reasonable, but it's still not the correct answer, and it's still below the score. Then we have, another example. We get another nonsensical answer here, but since this is a competition, other contestants are producing answers. Okay, so we have the answer here is June. Here we have November, here we have May. Okay, the system can now see the pattern that actually the answer type is not a day, it's a month, and then with this change of the answer type, it is correctly able to guess that, the other two answers which are correct, and at least recover some points in the game. All right, so this is another another example of of the architecture sort of on the logical level. So again, what you saw before was that we had a question coming here. We analyze it with respect to the topic, what is the question about and what is the answer. We decompose the question if necessary. We use search to generate a hypothesis. And then we score the evidence and we provide the final answer. So for all of that we need a parallel system because we have hundreds of sources. From these sources we generate many possible answers, many possible candidates. Then we sort of take, say, the top 200 ranked by a search engine. Each candidate has associated thousands of pieces of evidence, because we look actually at the paragraphs that describe these candidate answers in different sources, and for each of these paragraphs we ask the question, does it contribute to the answer? Does it connect the answer with the question? All right? Well, so we get hundreds of thousands of scores, and all of that has to be then, the numbers have to be multiplied and added to create the final answer. So that's essentially what's happening. Now, why were we able to be successful in this project? I mean, there are many reasons, but one of the reasons has to do that we have a gold standard. Jeopardy questions from, I think, 1950s until the most recent shows are available on a website called Jeopardy, and this is everybody can download these questions and try to use them for the question answering system, so there are no legal restrictions on that set. So we had at the beginning, from the beginning, about 200,000 questions with answers. So this allowed us to essentially leverage this kind of architecture where we can generate, we can create hundreds of candidates. For each candidate we can generate multiple pieces of evidence, yes, multiple scores, and then somehow aggregate these scores. So to know, for instance, how good is Wikipedia, in answering questions about history versus, say, a World Book Encyclopedia, you have to know, you have to have some prior knowledge, yes, because we're gonna score not only sort of the relation between the entities, but also the provenance, yes, we're gonna score the source that it's coming from. If we get a source that mentions certain entities together, but it comes from the web, from the Corpus Expansion that we do, we very likely gonna score it lower than the stuff coming from Wikipedia or some other encyclopedic-like source. So that's essentially what we can do. That we can take 10,000 questions and we can create the weights on this synthesizer, on this hypothesis, evidence, and scoring, and then provide the final answer and adjust the weights on these scorers based on new evidence and new questions that we are playing with. So we have run cases. There were about 20-something people involved in the project. We have run about 10,000 recorded experiments. That is, we know for this experiment which questions were correctly answered and for what reasons. That is, we have the scores, we have the supporting passages that link the scores with the candidate answers, and well, we can see whether the performance is improving when we add a new module, and we could see if the performance was improving, say, if we added a new encyclopedia. Okay, so all of that could be measured, and we could see the project making progress, eventually sort of being at a place where we believed we were competitive with humans. So that's when the decision was made to do a real game. All right, so just to finish this introduction, in Watson we do not do data mining, we do not do predictive analysis, okay, and we do not make new knowledge discoveries. What we do instead is we connect different pieces of evidence trying to answer questions, okay. So essentially Watson is a complement to such capabilities. We focus on understanding the question, understanding the corpus that contains large volumes of text, and essentially you can think of a Watson as a huge evidence weighing machine. That's essentially what it is. So of course this means that it can be applied in other places where evidence weighing is important, and that's where possible commercial applications will be. So, all right. I was mostly involved in preparation of textual databases for Watson, and there is a couple of interesting observations and a couple of contributions that are worth mentioning. I'm going to go through them relatively fast. All the information about Watson technologies is available from the IBM Journal of Research and Development, and it is published, it's available from IEEE.org. Okay, so if you type Watson there and IBM R&D, you should be able to get to the sources. If you can't, or if your institution doesn't have a subscription, send me a note. I'll send you a zipped file with all the papers. All right. So it turns out that if you take Wikipedia and you take Wikipedia titles, okay, around 95% of Jeopardy answers are Wikipedia titles. Well, there are about 4 million of Wikipedia titles, and in particular, there are all numbers, I don't know, from 0 to 100,000 represented there, so it's not that surprising, yes? And it doesn't mean that the article itself would be the right answer for the question. It just means that, that string is represented as a title. But that observation was essentially a starting point of using titles as answers. That is, we're gonna assume that except for some puzzle-like questions, we will answer the questions with a title of a document, okay? And that creates certain problems. I'm gonna talk about it in a minute, but essentially this is an innovation that I think we probably were the first one to do so. And it turns out that this allowed us to increase the precision of the system quite a bit. We had an iterative process to ensure the quality of dealing with textual sources. That is, source selection, source preprocessing, source transformation, corpus expansion, all of that were sort of carefully paired with the process of error analysis, okay? So just a few words about source selection. Well, we had the list of questions, yes, so that we are trying to answer from some prior Jeopardy games, and say we could see that we are not answering questions, I don't know, about Shakespeare, yes? We could investigate whether the problem was lack of sources or whether the problem was that we couldn't understand the language. And then we could make a decision that maybe we should acquire, say, complete works of Shakespeare and add it to our corpus. Once this decision was made, well, we could, plug in the document from Gutenberg.org, yes, and see if there was an impact. Well, there wasn't an impact because it turns out that even though technically the data was there, we were unable to get to the data, and we had two choices: either to improve our language processing capability or to change the source. So essentially, in most of such cases, we would change the source. So we would do, we would take the source, run some experiment, and finally, after these experiments, create a version that would work best with the existing system. All right, so we used Wikipedia for facts, okay? We also had some dictionaries like Wiktionary. And to that starting point, we added several other sources. So we added other encyclopedias. We added a collection of song lyrics because there is a lot of stuff on songs in Jeopardy questions. We also tried to add various other sources, like a complete collection of from Gutenberg, and that didn't work so well, for instance. And there is prior work in that space where it turns out that adding data doesn't necessarily improve performance of question answering systems. So we ran quite a few experiments adding sources in different formats to get to the place where we were. We had not only a problem of just finding the right sources, but also we had a requirement that we needed a system that would be standalone, that is not connected to the internet, and that would answer questions in less than 3 seconds, and very often much less than that. So we add a source, and what we do next is we run an experiment. So this is some snapshot of a tool that we use to run an experiment, and essentially this is a list. So as of February 2011, which is more or less right after the game, we had about 9,000 experiments fully recorded in the tool. And what you can do is you can compare two experiments and see the differences in performance, how many questions did we get correctly, or the particular corpus of questions, how many incorrectly, did we get any answers, correct answers in the second or third place. All of that stuff will be investigated. We can look at the evidence, so I'm not going to go into it. But the process was very important because that way we could quantify any addition or subtraction from the system. So I mentioned before that we decided to add Shakespeare, yes, complete works, but questions in Jeopardy are not of the sort, okay, here is a quote, tell me which play it is from, or here is the quote, tell me who said it, okay? Or sometimes this is required as part of this question transformation into two pieces. So what we did, for instance, was we divided the works of Shakespeare into several corpora in which all quotes from all Ophelia's quotes were in one document with the title Ophelia. So if the question was, had some segment of show me the steep and thorny way to heaven, and then we could answer Ophelia if the question was about, which character said it. And we had another title, William Shakespeare, for a similar quote, and it would say, and the title was William Shakespeare. That would be for the question, which of the playwright said something like that in 16th century or so. So we did that. We did this with, with Shakespeare. We did this with Bible, with a lot of important books. We did it with IBM marketing campaigns because occasionally there are questions like that. In Jeopardy, with song lyrics and poetry. So that was, quite a bit of data transformation and preparation. But that essentially allowed us to avoid going into very deep language understanding that otherwise would be required. Some other stuff that had to be done was normalization of spelling, normalization of names, which is a very difficult task. We normalized based on Wikipedia, so therefore, some titles like Duke of Normandy had to be dropped. Dates had to be normalized because depending on the source, 08 might mean 1908 or it might mean 2008. And we did, various kinds of extractions from Gutenberg Corpora, from wiki quotes, glosses from WordNet, and all that kind of stuff to prepare the sources. Another thing is that we very often try to estimate the sort of conceptual distances between the question and the possible candidate answer. And one of the tools was a collection of n-grams created from about 200 gigabytes of text. We pre-processed it. A number of experiments was run, but eventually it was pre-processed in paragraphs. We ran experiments with different frequencies, with alphabetic and not alphabetic orders, with term and word-based n-grams. And the result was that we got a tenfold reduction in size, which was important since the system had to be standalone, with the same or better performance that we would get from Google n-grams. All right, and the final thing here that I want to mention is Corpus Expansion. So, despite the fact that we had a number of encyclopedias, Wikipedia was a big source, we could not always find the right information, or if the answer to the question was in some source, very often the pieces would have to be put together that would require too much intelligence. Okay, the system is not intelligent enough to take pieces of information from completely different sources and always reliably put them together. So what we did instead is we started with a collection of most popular Wikipedia titles. We went to the web and we crawled information. So we crawled, say, 100 or 1,000 web pages that were the top answers, the top on the list from a search engine. Okay. Then we went to this website, downloaded the web page, scored each little paragraph or segment, and then added it as so-called pseudo documents to the corpus. Okay, with the idea being that some novel combinations of important concepts about a topic such as, I don't know, King Lear, yes, might appear in some of these nuggets, and that would allow us to find this kind of a document relatively quickly, to connect some missing links without the ability that humans have, that, to essentially do full deductive or inductive reasoning. So we evaluate, okay, so essentially this is the process. So we look at the seed document. We have Tourette syndrome is the topic. We find a collection of documents on the web here. We divide it into pieces that you can see here. We score the pieces. We delete certain segments, which are, for instance, advertising would be deleted, or segments that do not bring anything new compared to the original source. And then we create, this particular pseudo document, and we add it to the corpus. And after that, we evaluate it. I don't know why this is not coming, but there was a slide here with a table which shows on my computer. I don't know why it doesn't show here. But anyway, all right, well, sorry about that. I mean, it's summarized in the article on source engineering in the IBM R&D journal, but the bottom line is that there is a cost associated with adding sources. Okay, and the cost has to do with the fact that that you get more data, you get say 1 order of magnitude more data if you add some additional encyclopedias and some other sources. When it comes to corpus expansion, you can add many orders of magnitude of such data. So the final collection of data was probably on the order of around 60 gigabytes. That is raw text. Keep in mind that we needed much bigger storage capability on the system because all the corpus was pre-processed. Okay, we didn't do real-time parsing of the corpus when answering questions. So the parsing happened offline. We stored the corpora both in the textual form and in the parsed form, so that when doing a comparison of predicate argument structure of the question with the predicate argument structure of a passage, we could do it really, really fast. The questions were, of course, parsed because we didn't know what the questions were when the competition was run. So they had to be parsed and properly processed, but it's relatively easy to process 20 or 25 word questions than to process in real time, a large Wikipedia article. All right, so sorry about that. All right, so let's see. So what did we learn from that? Well, a large part of, it's like with data mining, a lot of effort has to go with data preparation. So indeed, that was also part of Watson, a substantial part. We came up with a few interesting ideas. How do we go about evaluating knowledge gaps? That we're going to use title-oriented answers, various methods of source transformation, corpus expansion, and the iterative process of monitoring the impact. So this is applicable to new domains, and we are applying it right now to medicine, help desk support, and finance. So I'm going to say a few words about that. And since I'm being told that I should hurry up, it's going to be fast. All right, so that's the history of the project. I mentioned it started more or less around 2006, in 2008. The Jeopardy show was transmitted in February 2011. Around August 2011, we made the decision that we're going to focus on medicine-related applications for two reasons. One is it's a big problem for the society. Second, it's a very big and challenging problem for NLP, and we're going to see a little bit why. We are toying with some other ideas like Watson for financial services. So there colleagues are involved in that. I am more involved in creating a solution for call centers, where somebody calls with a problem, and currently the agent either has to know the solution or has to search for a solution. This takes a lot of time, and altogether it's a very expensive process. So if we could do it faster, then of course the time would be shorter, you could cover a larger collection of problems, the solutions would be better, so that's why I'm interested in this particular problem. And it's more manageable than medicine, I think, at this stage in the game. At least the language seems to be less challenging to me. All right, so medicine. All right, so the idea is very similar here. You have a collection of symptoms, and you want to know what it is that is wrong with you. Yes, I mean that's why you go to the doctor. I mean, we are not trying to build a robotic doctor, but rather what we are trying to do is create a support system for the doctor where, based on a collection of data, the system can suggest some stuff that possibly the doctor may be missing, and also assign some evidence profiles to various possibilities. Okay. And what you saw in this animation was essentially that sort of this final answer, yes, urinary tract infection, the confidence in that answer, yes, or the probability that this answer is correct based on the data that the system has changes, okay? It changes based on family history, patient history, findings of medications that people take. So essentially, such system would have to be interactive. Yes, we saw it, in a very small, in miniature. Yes, when the system was learning from previous Jeopardy question. Here we are extending it to add different types of information, and essentially adjust the weights dynamically as new information comes in. Okay, so that's the vision, and some of it is already a reality. But of course, we are still. I mean, this is still a research prototype. We do have, however, some partners. Okay, so we are talking to WellPoint about providing some sanity check for some of the procedures that are advocated by the doctors, okay, to improve the quality of care. We are talking to Sloan Memorial Catering Center because there is a lot of data about cancer, and being able to get to new data and connect different pieces of data, as we saw in Jeopardy, might be of some value. And now, on the research side, we are trying to essentially add some other stuff. So we have to deal with medical knowledge, that's obvious, but we also have to find information from other sources, like medical health record, yes? Plus, we need to do something with the diary. So the challenges that we see here are many, okay? So what is an answer? Yes, in Jeopardy it was very simple. It was, a string. In the medical field, well, really, I mean, the answer at best, okay, is what you saw there, sort of a collection of possible, diseases with some evidence profiles for each of them. But for instance, when you deal with customer support, the answer is neither of these. Yes, very often it's a procedure. Yes, you have to find a procedure that solves the problem that the customer has. Medical domain is difficult. The language is difficult. So we have to deal with the vocabulary. So we're trying to normalize it very often based on UMLS, which is the medical language system, which has thousands or millions of terms. We have to adapt the algorithms. We have to incorporate other kinds of knowledge. I mentioned that, add dialogue and deeper reasoning capability. The Jeopardy system had very shallow reasoning capabilities because we didn't know how to control sort of longer chains of reasoning. Here we would like to do it better. So in other words, we have to do deeper NLP. So here is some illustrations. I know I will do this very fast. So what is an answer? Yes? It turns out that if you take a domain of medical questions, there is a similar competition to Jeopardy called Doctor's Dilemma, and you run it through a Watson system, we get many more answers than what is deemed to be one correct answer. And when you ask doctors, okay, they can say that some of these answers are actually acceptable, that would be a correct that hypothesis, but of course it's not in the system. We can train our system until these answers are vetted, so until they are checked by the doctors, and only then we can adjust our scoring capabilities. Domain adaptation, okay, or text, dealing with text properly. So you can see two curves there, one with and the other one without domain adaptation. So we add we answer more questions, of course, if we do some proper text processing. Training, so adding, say, starting with the system without any training, or weights being trained, say, on the Jeopardy system, is not good, okay? So you have to train on medical system, and you get sort of a big bump out of doing proper training. You have to go deeper into language. I don't have time to go into this chart, but essentially what you see there is, on the left you have a question, and on the right you have some linguistic expression which is related to the question, but you see that the words are completely different. So how do we make the connection? So doing more of this adaptation, essentially we can measure, again, we can measure the progress of the system. And what you see there is, I don't know, this is the curve from a couple of months ago, I think, that sort of shows the performance of the system on the Doctor's Dilemma questions. All right, so I guess last slide. We have Watson is being used to address questions in NLP for medicine, and we are trying also to apply it to customer support. We have new sets of challenges there, so different concepts, different vocabularies, dealing with dialogue, new ways of scoring. We talked a lot about carefully preparing the data, trying different algorithms, and finally, we believe that with this methodology, and by addressing this collection of challenging practical problems, we contribute to the growth of the language understanding, okay, and this provides sort of an interesting perspective on human language technologies, okay. I mean, the domain is not sort of the common language. Nevertheless, the challenges are real, and the contributions, well, seem to be also real. So I'm going to stop at that and answer some questions.
Okay, there's still time for a few questions.
I have a question. Neither the Jeopardy nor the medical application that you showed is classical QA, right? It's
Yes.
for both of them exactly what you try to do with semantic QA, namely the Q part, making a very sophisticated large coverage Q is almost impossible, because the question part, yeah, so in Jeopardy you get very strange syntax, these clues, and so you cannot even have full coverage. Yeah? So,
Yes.
but then it seems that for these applications like Jeopardy and medical, it's much more important to get lots of clues basically right than to understand. Is in the background, because it's called deep QA, is in the background for other applications also some, we have some large coverage, highly specialized, domain specialized question analysis that you couldn't use here? Or is that that you only go for domains where you get more the clue type questions instead of the real questions?
No, I mean the questions, I mean the Jeopardy questions, despite the strange syntax, are real. I mean this is, you know, instead of asking, you know, this person, you can ask who, yes? And this would be a very simple syntactic transformation. So, so from the perspective of question answering, this is a real question answer. And the reason it's deep is that underneath, okay, I mean I talked mostly actually about the shallow part, but underneath there is a very large coverage English grammar, okay, and the parser. So I mean, I mentioned parsing before, that you know that we actually pre-process all these corpora and you know assign predicate argument structure and connect it with you know some semantic entities as far as we can. Okay, so that's the deep part. And the vocabulary for Jeopardy is the common vocabulary of an educated person in the US. And the reason the questions are formulated that way, that is, they are formulated as answers, yes, has to do with with being funny and being entertaining, all that kind of stuff. But linguistically, it is a simple transformation, so we don't have to do much. For medical, we actually do have to substantially change the parser because the vocabulary, the syntax of the medical domain is different. It's the same core, but it needs substantial additions. I don't know, did I answer your question?
Any other questions, comments?
Okay, so you said that you applied it to medical texts.
Yes.
How did you cope with Latin inside? And there's, of course, multilinguality question behind that.
Yes. I actually don't know how we cope with Latin unless the Latin is in some dictionary. Okay, I mean many of the Latin words are embedded in UMLS as concepts. So if it's there, we have it. If it's not there, we don't. Okay, so we do not address multilinguality as such. We assume it's all English. It's just sometimes it's strange English.
Okay, any other questions? I actually have a question I can't stop myself from asking. You mentioned that there's some deep parsing within the system. Can you say a bit more about it?
Yes, so the grammar that we use and the system that we use is English slope grammar. It's been built by Michael McCord. He started working on it, I think, in the early 80s. And it's arguably the best existing parser of English. What else can I say about it? It is large coverage. It provides you both with the syntactic parse and with the best guess for predicate argument structure. It's not perfect because no parser is, but it's good enough for us to both deal with Jeopardy questions, which sometimes, I mean, they have some challenges, but we are also able to do a reasonable work on parsing on parsing large corpora where you have long technical sentences, and very often the structure is right, and even more often the pieces of the structure is right, and that allows us to, to match the predicate argument structure of the question with the predicate argument structure of the supporting passage. And again, this doesn't have to be perfect, and it almost never is perfect. So depending on the degree of match and some other circumstances, all these evidence weighing mechanisms allows us to, to decide, is this a good piece of evidence or not? And it happens often enough that we can win the game. That's basically what it is. It doesn't have to be perfect.
Last question.
So at some point you said that Watson doesn't do knowledge discovery.
Yes.
But then you gave this example of synthesizing information. So
Yes.
doesn't that verge on knowledge discovery? Isn't there some potential for that?
Maybe it verges, but it only happens because it's a question, and it happens because we can't answer, we don't find good candidate answers otherwise. So essentially, we employ the parallel strategy of decomposition, and in some cases, the composition wins. But really, we are not trying to discover new knowledge. Although in medicine, we do need to find now these missing links. Yes, we want to connect, say, the disease to treatment, or disease collection of medicine to possible side effects. So these chains of reasoning there are deeper, and we are investigating various ways of controlling this process of inference.
Yeah, I'm afraid we really have to stop here.
All right, so maybe